For our next example of undetermined coefficients, we'll look at this one, y double prime plus 4y equals 3 cosine 2t. So our first choice for a guess for this one would be that y should look like some cosine 2t terms, and then, not repeating the mistake that we made last time, also include some sine terms to account for the derivative of y when we stick it into the equation there. So let's see. So then if we apply L to this guess for our particular solution, we're going to have the second derivative of this, so this would be minus 4a cosine 2t minus 4b sine 2t. So that's our second derivative. And then we're going to have plus 4 times the original thing, a cosine 2t plus b sine 2t. And so that's our original guess. And then this is supposed to be equal to our forcing function, 3 cosine 2t. All right. So now we draw up the equations for the different terms. So let's see. So adding up the signs, I see that there's minus 4 signs here and positive 4 b signs here, and so those are going to cancel, and so then that just leaves me with the cosine terms, and then I notice that there's minus 4a of them here and positive 4a of them there, and that cancels, and so that leaves me with 0 equals 3 cosine 2t, which is clearly wrong. So that's not good. Okay, what went wrong? So somehow we had a bad guess. Well, to understand what went wrong with this guess, we need to look a little bit under the surface. So once upon a time, I told you that whenever you're solving one of these equations, you need to solve for the complementary solution first. And in fact, if we had done so here, we would have not had this mistake. So let's find the complementary solution. And so for that, let's see. So our characteristic polynomial is going to be r squared plus 4. And so that one tells us that, so we're going to get complex roots here. So r is going to be plus or minus 2i. And so our complementary solution is going to be c1. And then since the real part is 0, that means that the exponential part does not appear. So it's just, because it's the exponential, e to the 0 is just 1, right? So cosine 2t plus c2 sine 2t. So we've identified the problem. So the problem is that the forcing function duplicates a complementary solution. And so what happens here is that we need to go somewhere else to find a linearly independent solution. So what to do? Well, the fix that I told you before is if in doubt, strap another t on it, and it works. So again, this is a version of reduction of order. that makes it work. And so our new revised guess is going to be AT cosine 2t plus BT sine 2t. And then we need to take into account derivatives. So we would include like a C cosine 2t plus D sine 2t. At least we would in general. Now, it turns out that this is, because of this problem, this guess is based on the fact that there's this duplication of the complementary solution. This part, again, will also duplicate. And as a consequence, any component that we get from the just cosine 2t and sine 2t terms can get grouped in with the complementary solution. Long story short, just forget it. You can include it, you'll get the right answer, you'll just end up doing a lot more algebra than you needed to do. I can guarantee you those parts will cancel out or be absorbed into the complementary solution. Okay, so let's see now. So now when we do so if we take this new guess and we feed it to our differential equation, then what do we have? So the second derivative of yp now looks like minus 4a sine 2t minus 4b t sine 2t plus 4b cosine 2t minus 4at cosine 2t. And then we've got y itself, so at cosine 2t bt sine 2t. And so collecting all this junk together, on the left-hand side, we're going to have our forcing function, which was 3 cosine 2t. And on the right side, we have, well, let's see there. So we actually have a whole bunch of cancellation, it looks like. So let's see what cancels out. There's the AT cosine terms. There's minus 4 here and plus 4 here. And then there's the BT sine terms, and we've got minus 4 of them here and plus 4 of them here. And that looks like it. Okay, so we have minus 4a sine 2t plus 4b cosine 2t. And so we have the equation for the coefficients of sine 2t, which is minus 4a equals 0. And then we have the equation for cosine 2t, which is 4b equals 3. And so then that tells us that a is equal to 0, b is equal to 3/4, and so our particular solution is going to be 3/4 t sine 2t. B was the coefficient of the sine term. Yes. Okay. Good. So that's this one. And I just wanted to point out, it just crossed my mind, the reason why we are able to make this step and go from this equation here to this equation here, to this system of equations right here, is we're actually using linear independence. And I mentioned this once a long time ago, but I'll just say it again because it's useful to see what's going on here. So we have minus 4a sine 2t, and then we have 4b minus 3 cosine 2t equals 0, right? So I've just rewritten this equation here in the green box, and I wanted to write it as a dependence relation, right? So we have a linear combination of sine and cosine that adds up to be 0, but we know that sine 2t cosine 2t is linearly independent. We checked that with the Wronskian and so on and so forth. So the only way that you can have this is if all of the coefficients, so minus 4a and 4b minus 3, are all equal to 0. And so then it's exactly these equations right here that we solve in this system. And so that's linear independence.